So last time we introduced review of solid mechanics. So I made this video right here. I hope you watch it. And then a couple days later, I talk about mechanics inside a beam. And that one is here. I hope you also watch it. If you need PowerPoints, they are here, the same PowerPoint. And also, if you are not comfortable with English, I have several videos in Chinese in the past. You can watch them if you enjoy Chinese more. That's fine for me. So today we are moving on to the next portion of the lecture. So in today's lecture, there's only 10 slides. But we need to practice how to solve a problem like this. Okay? This is good, okay. So this is important because later on during the exam, I will give away one problem very similar to this. Of course, the geometry and how the loads are being applied to the shaft will be different. So please make sure you know how to do it. And you have learned this in the past, but at the second half of the problem, you will use some of the knowledge based on this lecture. Okay? So that's why I feel like this problem solving is important. This is going to be the fundamental of doing mechanical design. So let's look at this shaft problem. There are two bearings at both ends of the shaft, and there are two pulley wheels right here. And the left one is being pulled along the along the Z direction, being pulled this way, and this one is being pulled up along Y direction. Okay, so we need to solve for reaction forces everywhere, and also we want to see the shearing force and moment, bending moment, inside the entire beam. And we are looking for the worst loading position, meaning at which position we are under the maximum load. If this position is having the maximum load, we will design this shaft based on that point. Because if the worst loading position can survive the loading, then the entire shaft can survive the load, because this one is the worst one. And once we determine which position is having the maximum load, we will plot out the Mohr circle of that position, and then we could calculate the principal stresses, maximum shear stress. With principal stress and maximum shear stress, we can do mechanical design. Okay, so my exam is always like this. A figure, some wording to describe what the figure is about, and several questions. And for this subject, usually the problems are the same. No matter how it look like, I usually ask you, okay, what are those? So it's an important problem. I'm sorry you cannot see it in the book. I made up by myself. Not exact. There's no exact same problem in the book, but there are many similar problems. Okay, so over here we have distributed loads because for pulley, it's a belt type. It's a belt, so it's not like a single point load. It's not like a concentrated load. It's a distributed load. So the way this problem is describing the distributed load is to provide you Newton per millimeter unit. So if you want to calculate the overall load concentrated at one position, you need to multiply, use this linear load multiplying the width. So that's something people may forget. Okay, and over here, W1 is 5 Newton per millimeter, W2 is 7. So let me write it down. This is 5, this is 7. So it's having, if you use 7 minus 2, then you are having a sum at the end of positive 2, clockwise. So it's like it's generating some moment. 2 and times the width. 2 came from 7 minus 5. The unit is Newton over millimeter, and the width will be 50 millimeter. And also the radius. The radius is how large? How big? Okay, the diameter of both pulleys 75. So this is 75 over 2 millimeter. So this will be the moment that is generated at this point because of the difference of the pulling force, the tensional force from one end to the other end. For pulleys, it's always like that. One edge is having greater tension, the other one is not. And over here, let's take a look at this one. This is 15, and this one is 13. So this one, similarly, is having a moment following a different direction, and overall, it's also having 2 times 50 times 75 over 2. The moment is this big, okay? So it's reaching a balance of twisting moment. But even it's under the balance of the twisting moment, the material inside is being twisted all the time. Okay, and let's assume this tension force is always there, even when this whole thing is operating, is rotating, but the tension force is always there. So even this material is spinning, but every material inside this region is being twisted all the time. Okay, so please be aware the material inside is being twisted due to these two pairs of twisting forces. Okay. The problem doesn't tell you what are the reaction forces, so you have to use balance of forces to determine how large they are. And I think we ignore the weight. We don't care about the self-weight. So what are balancing with the reaction forces? Those four, the pulley forces, okay? So that would be pretty easy. We can move on to the next slide. It actually gives you everything that you need. First, this one is doing, okay, it's using balance of moment, okay? So I think this one, the first one, I'm using times 50. I need to know where I put the center. 10 plus 80 plus this plus. Okay, so the first equation, I chose this point as the center of my analysis. And I am working on the XY plane. So what's happening on the XZ plane has nothing to do with the first part. They are independent. Okay, so for the second half, is the analysis on the XZ plane. Oh, by the way, if you need PowerPoint, I think it's already there. Let me double check. Should be this one. Should be this one. Okay, let me double check if that's the right one. So if you need to take notes, yes, this is the one. Okay, so it's on the web page that I gave you earlier, and on the column, on the row of mechanics of a ship solving. Okay, so today we're solving this problem. So let's get back to what I'm having right now. So for the first part, first equation, I'm choosing this as a center. So only W3 and W4 facing up is generating a counterclockwise moment. So multiplying 50, because this is the unit of this is Newton per millimeter. So here is the millimeter. So after we do that, we have concentrated load in the unit of Newton. Okay, and then the distance from this point at the middle, so here is only 10. Okay, the center I'm choosing is right at the center. And also when we concentrate the distributed load at the middle, then we are analyzing at the middle of this portion. So over here, the distance is 25. That's why here is 10 and here is 25. Okay, so please make sure you get this right. And RFY would be this one. Reaction force along the reaction force at point F along Y direction. And the distance will be just over here, this one is 10. Half, okay? So that's why this is 10. Similarly, for the second equation, I think I'm choosing this position as the center. So over here, I'm using 10 plus 80 plus 25 as the distance. This is computing the clockwise moment about the center F. And over here, we have RAY, this guy. It was drawn facing up, so it's also having a clockwise moment. So use RAY multiplying the distance between A and F. This is the distance between A and F, Right? So by solving those two, you can get these two numbers. When you solve a problem like this during an exam, please make sure you highlight which one is your answer. And please specify this is an answer for which subproblem. Because your answer sheet will be very long, several pages. It's very difficult for us to find where exactly your answer is. So please specify, highlight, okay, this is answer for A. Okay, now similarly, we are solving on the XZ plane. And using the same trick, we are able to get RAZ and RFZ. Okay, I'm not going to go through the procedure again. Okay, everyone okay, right? This is only statics. Okay, so just balance of moment. Okay, one question. So if I have a portion, and then I have a shape like this, and let's say this distance is L, and let's say this height is W. If I want to convert this into a concentrated load, does everyone remember how to do it? Anyone? Concentrated load. So suppose it will become somewhere like here, concentrated. But where? And also how large? Anyone remember? Yeah? 1 over 3 of
right hand side.
1 over 3 of L?
Yes.
Okay, so here is, yes, L over 3. Thank you. So what's the magnitude? How large?
W times L.
Okay.
Over 2.
Over 2, yes. So basically the integral, the area of this shape is how much concentrated load it will be. Okay, so for any shape, just calculate the area. Then you can convert this into a concentrated load. And where is the position of it? Right at the center of the geometry. Okay, so for triangles, the center of the geometry is having 1/3 of the distance along one direction. Okay, so thank you, very good. Please make sure you guys know how to do it, because later on we may have different shapes. We could have a circle, rectangle, any shapes. Then you need to know how to convert this into concentrated load. Okay? If you forget, go back to statics. In statics, we solved many of those problems in the past. You guys okay? Thank you. So next, to get the shear force diagram and bending moment diagram. The way I like to do it is to draw the shear force diagram directly. There are many ways to solve this, but if you use this way, I feel like is the easiest one. Right now we are analyzing this along which direction? Okay, along the XY plane. So in this page, we are analyzing on the XY plane. Okay, so this plane. And we already know I have this. Okay, this is what we had earlier. So this one is actually going down 435 Newton, And this one is actually going down 965 Newton. Okay, I'm rounding them just for short, for simplicity. Okay, so we have concentrated load here. So over here we have W3 plus W4 multiplying 50. We have concentrated load there. And there's the size of them. Oh, we cannot do, we don't concentrate them at this point, sorry. We don't concentrate them. We should say over here, overall, we have distributed loads. And the total distributed load will be W3 plus W4. And the amplitude of them will be 15 plus 13, 28. The unit is Newton over millimeter. Okay? So the way to draw this directly is to take a walk from one edge to the other one. So I start from this edge at the center point. Actually, I start from the very end, right here. So this is like where my bearing is. And over here, we assume, we assume there is a concentrated load pointing downward. So when I'm right at the center of this point, I know there's a force pulling downward, 435 Newton. So you just make a drawing of this, and because it's going downward, so negative 435. So then continue to walk. There's no more force, and you are going to make a straight line until you reach this point. This is where you are first time seeing this edge of this distributed load. So this is at the position of D. At the position of D. And since it's having a distributed load, and it will pull up this diagram little by little, and the slope of it is 28. The slope of it is 28. Okay? So it's going up. Every millimeter it goes, the pulling force increases by 28. Okay, and when you are reaching this point, this is point E. No more force at the right edge. So this shearing force will have a horizontal line from point E down to this point F. Here's point F. And we have a downward force of 965. And you will find this exactly right. This should be 965 going down. If you use this trick to take a walk from one edge to the other, and this force doesn't go back to zero, something was wrong. Maybe you made some mistake. And in many times, because we are not giving you proper numbers, you may need to do some rounding. And you may have several digits different. That's fine. Don't worry too much, because I was doing rounding as well. So you may not reach exactly zero, a very tiny difference. But if you can, try to calculate everything properly. So in the exam, you may want to make a drawing like this and specify where they are. Like, tell me what's the distance right here. Tell me what's the distance right here. Tell me where exactly you draw them. So just to indicate how you indicate that you know exactly what the shearing force look like. Okay. So this one should be okay, right? Now, because we have this relationship that I show you in the video, if we take integral, if we take an integral of v, then we can get moment. So on the right hand side, I try to derive the linear equations of my shearing forces at different regions. And they are very easy to get because they're just straight lines. So this one, obviously within this region, it's negative 435. And within the other region, it's a line. The slope is 28. And I have a constant right here. I can actually plug in any point to get C. This is what I did right here. I plug in 240, and I should get this value. This is how I calculate C. Okay? And for the third region, it should have a shearing force of this number. Okay? So once you have the drawing, the next step is to formulate the linear equations. Because later on you want to do integral. If you have equations, when you do integral, it's much easier. Okay, so I feel like the trick is to make the drawing first. The first step, make the drawing. And then the second step, formulate the linear equations. Then in the third step, do the integral. Okay, and when you do the integral, because they are linear equations, they are polynomials, it's very easy to do. But remember, you need to add those constants. Otherwise, your function could be located at different positions. So when you do integrals, you need your constant term. The constant term could be anything. You need boundary conditions to solve for those constants. So here, from here to here, we get the integrals. So we get moments. In here, this means over different in different regions, we have different behaviors of bending moments, and they are having different shapes. This one, the first one is telling you, okay, it's gonna be a linear function, which is having a negative 435 slope. Okay, and the third one is also a linear function. It's having a slope of 965. Okay. And for the center part, it's going to be a second order polynomial if you do an integral from here to here, and supposedly it's gonna look like a curve. Okay? And if you later on we may need to solve for the minimum, the worst one right at the center. But not right now. So once you have those integrals, you need to apply several boundary conditions. So the first two conditions that we use was, the first one is right here. Because right at the edge, there's no bending. There's no material on the left-hand side. And there's nothing trying to, no twisting, sorry, there's no twisting. And also no bending. There's nothing that is trying to bend the. And how do we get C3? Because we need this linear equation must be followed. So we already know C2. We can then plug in this equation and then try to calculate what's this. Okay, so we plug in 240 on the first equation. So at the end, we have this number. That's how we can realize the bending moment over here is this number. Okay? And we can use it to plug in to the second equation. So in the second equation, right at the position of 240, and we have an unknown C3 right there, we can get C3. Okay? And for the last one, just the way I did it was just plug in. Plug in 290. Plug in the second equation using 290. And over here, I realize the bending moment right at this point is this number right here. And plug in the final equation. Or what I did was I used this guy to get the C4. So I was using the position of 380 to get the last coefficient. Of course, you can try to use the last equation and position 290. Plug in here to verify if the moment is truly this number, but I didn't do it. You can do it. It should be right. Okay, so at the end, this is how the entire bending moment diagram look like along on the XY plane. Okay, so this is how this shaft is being bended on the XY plane. So what's the shape? If you analyze in this way, you are treating supposedly positive bending moment represent supposedly right-hand rule is going this way. So since this is negative, it's going this way. Let me double check. If we have a shaft like this, and we're doing this. Yes, we're doing this. Okay. If we pull up, then our shaft bends in this way, right? If we pull up from here and support on two edge, we are pulling up in this way, so this shaft is bended in this way. So in order to bend this shaft in this way, the only possibility is to have bending moment following this direction. So we are analyzing our right-hand side. So for every cut, we're analyzing what is the moment on the right edge of the position of our analysis. And I'm trying to match our drawing to the reality to see if we are making sense to our results. So right here, usually we follow the right-hand rule. A bending moment about Z axis should be positive. So that means if we have bending moment going counterclockwise, it should be positive. But over here, as a result, we have negative bending moments, which means our moment is going this way, clockwise. And this is matching what we observe onto the shaft. Okay, so I encourage you to always think about what you are calculating and also what does each calculation represent on its orientation. Is this part okay? And this is
still review of what you have done in the past. But in the exam, you need to try it multiple times. And I wish you, when you make a drawing like this, you can draw the diagram more accurately. Because sometimes when some students try to solve the problem in a hurry, they just draw an ugly drawing and then to indicate that he has drawn something. But he didn't draw at the right position, he just draw a curve, just begging me to give him some point. Please draw this precisely. Try to draw this as precisely as possible. Okay? Now, I'm moving on to the next slide. So we're going to repeat this whole thing again on the other plane, on the XZ plane. Okay, so let's move on to the XZ plane. Okay, so over here we have a force going this way. Let me see. Okay, because this is positive z. Going this way is positive z, but based on what we had earlier, it was negative. So the force right here is actually going this way. That was the negative z direction. Okay, it's going into the whiteboard. And also for this guy, it's going into the whiteboard. The magnitude would be 413 and also 187, 414. 414. Okay, and when I plot this diagram, I'm plotting, this is positive z direction. So going downward, this is negative z. So supposedly we should draw it downward. Okay, going this way will be downward in the diagram. So please make sure you make it right. Okay? So follow what we had earlier from the center point of the bearing going down to right here where we have the distributed loads. Okay, and this is point B and point C. So from point A to point B, we have a horizontal line, and from B to C, we have positive 12 Newton per millimeter going the positive way. So here is having a positive slope with a magnitude of 12 Newton per millimeter. And then when we are up to point C, no more forces along the on the XY plane. So the shearing force remains the same until it reaches the edge, and then going into the whiteboard with a magnitude of 187. That's how you end up with a shearing force diagram right here. Formulating the linear equations just like what we did earlier. Taking the integral, meanwhile solving for those constants with all the boundary conditions. I'm using exactly same trick, so I'm not going to repeat again. Okay? So overall, you guys okay with this? I'm not going to repeat this. It will take too long. Okay? So if you follow what we did earlier, you should be okay with this. Basically, same analysis, but along different plane. So once you have both, let's take a look at what's going to happen later. So you're going to analyze it by combining those two bending moment diagram together. So what's happening is there is a bending moment like this along on the XY plane, and also there is another bending moment, also negative side, so it's like this. I hope you understand it. Can you? Because it's a 3D diagram, okay, and this is going downward, right? I hope you can visualize it. Okay, so this is on the XY plane going downward, and this is on the XZ plane going into the wall. So this entire shaft is being bended individually along the Y direction and the Z direction. So let's pick up a point. Let's say there's a point right here. Let's pick up a point. Okay, so this point is having bending moment along this way and bending moment along this way. So if you combine those two bending moment together by adding those two vectors, it's having a sum of bending moment along some direction going this way, but you don't know exact angle yet unless you made some calculation. So this sum of bending moment vectors will tell you where exactly this point is being bended and what's the magnitude of that bending moment. Okay, so you'll realize this shaft is being bended along different directions everywhere. So now what we need to do is to figure out at which point we will have the largest bending moment. So the way I try it is to find what's the largest moment along Y and what's the largest along Z. So I was trying to find the maximum ones along Y and Z directions. So the way I did it was to find the extreme point by solving moment from equals to 0. Basically, the moment dx equals to 0. This is where you have 0 slope. And when you have 0 slope, you have your extreme point. So I was doing a derivative, basically the m dx, and then I consider this as 0. This tells me a position. So at the position of 2, 5, 6, I will have my minimum point of bending moment. But when we say minimum, it means value-wise it's the most negative, but amplitude-wise is the largest. Okay, so when I say maximum moment, it means I'm looking for the position that has the largest amplitude or magnitude of bending moment. Okay, and I plug in the position back to the second order bending moment equation to calculate how much moment that we will get at the end. So this is how you can calculate it. You just plug back the position. Similarly, I did the same thing for the z direction, and I got this magnitude. So it's like right here, right at this 134 point. If we visualize it from the side at x equals to 134, and if we draw this from the side, this will be my z direction, and sorry, z is going forward. This is my z direction, this is my y direction, and x is pointing you guys. X is pointing you guys. So right at the 134 millimeter position, I will have a bending moment going this way, and I have another bending moment going this way. So the sum will be this. So this one over here, this is negative 44341. And this one you need to plug in. You need to use 134 and plug in this linear equation. You can get it. And then at the end, you can calculate what's the total moment at that position. Okay? Oh, I was doing it in the next slide. I did it. I calculated. Okay. So I did calculate it. Okay, so I plug in to the linear portion right here. I get negative 54157. Actually, if I draw the vector along the negative direction, I don't need the negative sign anymore. Okay, and also right at this 256 point, 256 millimeter position, right over there. Similarly, I will have two bending moments. One is this one is 103462, and the other one would be I made a mistake. This is going downward, so this should be 54157. This is going backward, 44341, and here is 23210. Okay, do you get what I mean? So at different positions, they are having bending moments along two directions. You need to plot out in this way. Okay, you then calculate what's the overall bending moment you have. Okay? So I did. The total moment at 256, you can use the square root of the sum of the square of each vector. And then this is the overall moment right at the 256 position. We don't care about direction at this point. We don't need to worry about it. But if you truly want to know, it's going this way. So it's like this cylinder. There's a bending moment going backward. There's a bending moment going downward. So the sum is going like this way, along some tilting direction here. So this is how that point is being bended, going that way. So it's like if it's that way, because it's a negative value, it is going this way. If you follow the right-hand rule, it's like this. Is it? Yes, it's like this. So it's being bended like this way, along some angular, some tilted direction. It's not parallel to the XYZ plane. Okay, I hope you understand. So, at the position of 134, we use a centric, and I did the calculation. It was 6994. So this one is 6994. The sum of this at the end is 106033. So, which means at this position, we will have the largest bending moment. That's the worst case, worst condition. So if that's the worst one, are you guys okay? We'll just figure out where is the worst one. Okay, so next, let me erase what we had earlier. We now know where is the worst one. It's somewhere here. Somewhere here. This is the worst loading, worst or the largest bending moment. Okay, if we have bending moment, it will generate normal stress. Because we know stress equals to mc over I, right? So at that point, we are having the largest N. So the normal stress at that point is the largest. That's why we need to focus on that position. Okay. So we are doing this. In the past, we already derived how this equation equals to 32m over pi d cubed. That's why I asked you to memorize this. Then we know the stress, normal stress at that point is 25 megapascal. Okay, how about torque? Remember what I said at the beginning? It's always under some kind of twisting torque. And the problem doesn't tell you whether this twisting force is gonna reduce or not, or vary. It's always there. So if this twisting condition is always there, we will have torsion everywhere, right in the middle, right here. Okay? So the position that we found is also within the region where we have this torsion. So we just calculate how large the torque is. So what is 2? 2 is based on 15 minus 13. Okay, so there's a 15 minus 13, there's a 2 overall distributed load, and then multiplying the width, then we end up with a concentrated load. Multiplying the radius, we can calculate the torque. So over here, 15 minus 2 times the width times the radius. This whole thing is always under a torque of 3750 Newton times millimeter. And with that, we can calculate the stress using the equation. 16T over pi d cubed. Okay? How come the unit is megapascal? Because the moment that we are using is having a unit of Newton times millimeter, And over here we are using millimeter cube. So overall we have Newton over millimeter square. And if you transfer this into, convert this into Newton over millimeter, then you should have 10 to the power of 6 right there. And 10 to the power of 6 is mega, and Newton over meter is Pascal. The unit of pressure. Oh, sorry, cube. So this is how you end up with megapascal right away. So since you know we have normal stress and shearing stress right at this point somewhere at the top of the cylinder, it's actually somewhere right there. Okay, I try to show you where it is. It's like at some point above at the skin of this cylinder, somewhere, just following the direction of the total moment. Right at that point, we can observe a tiny element right at that point. You are observe it in this way, you will realize that tiny point is under normal stress going left and right, and a shearing stress due to twisting. And there's no normal stress along this direction because we only have pure bending and twisting. This is why we end up with this low diagram. So once we have this low diagram, we can use Mohr circle to analyze what's the principal stress. So this is what we get in the previous slide. We use the equation to get normal stress and shear stress. And we are sure this position is under this kind of low condition, and the normal stress will be the value that we get earlier, and the shear stress is like this. Then you can draw the Mohr circle. So we analyze this point first. It's having sigma and tau. You should draw a point at this point. So this is right here. Because I'm following right-hand rule, positive, counterclockwise as positive. This is going clockwise. So this should be this is actually negative. This is actually negative, going clockwise. So I should make a point right here. If this is the A point, this will be my A point. Then I move on to this position. If I say this is a B point, this will be my B point because at B point, we don't have stress, no normal stress, only shearing stress. This is going counterclockwise, so positive, because this in Mohr circle we are treating, in my Mohr circle I'm treating counterclockwise as positive. So once I change my view of my observation by 90 degrees over here, I should be making a 180 degree in the Mohr circle. So when I move on to point C, if I turn 90 degree again, I'm turning 180 degree back to C right here. That's why you got same normal stress and shearing stress. Okay, if you make a turn again, this is where your D is, and then you are back to here. E and D are the same. B and D are having the same low condition. Then you are sure your Mohr circle is correct. And over here, if you want to calculate the maximum shear stress, you basically want to calculate the radius of the Mohr circle. And last time I already tell you the equation is like this. If you wish to realize how, go back to the previous video. Okay, and this equation will be used a lot, so maybe you could kind of memorize it. But please be aware, this equation is only for this low condition. When this low condition changes, if there's normal stress right here, then the equation is different. So do not just memorize the equation and then assume it's always like that. This equation is like this just because that's the radius of the Mohr circle when you have a low condition like this. Okay? Please go back and review the online video, then you will realize. In that video, I also introduce a more general equation, and this equation will look a little bit different. Anyway, this is the radius of your Mohr circle, and over here, these two are the radius. So what you need to do for the first principal stress and the second principal stress is to use half of the sigma plus the radius and also minus radius, then you can get first and second principal stress. And that's how you solve the entire problem with this long process. Starting from the balance of moment, calculating the reaction forces, draw the shear force diagram, making an integral, draw the moment diagram, figure out which position is having the largest moment, analyze how much normal stress and shear stress this position has, and then plot out the low condition right here, draw the Mohr circle, calculate maximum shear stress, and also first and second principal stresses. That's what you need to do for your exam. Okay, so we are, I think today I would use a little bit time to introduce what we will be doing next. But for the next step, it requires more time for lecturing. So I will put that, I will be introducing several models. And I will put those models in the online video so you can watch them. But before you watch them, let me kind of remind you, let me review what's going to happen in the video. So if you have questions, you could ask me right now. Let's think about a material, a tiny material, and it's under tensile test. Okay? In my previous video, I actually tell you the Mohr circle of a tensile test looks like this. Because if you try to plot out the low condition of this material, there's only normal stress along this direction, there's no other stresses. Then you will get analyzing point along this direction and 0 point along this horizontal direction. That's why the Mohr circle of a tensile test is always like this. And at the beginning of the tensile test, when you are not applying any force, or when you are applying a very small force, the Mohr circle of this material is having a smaller size, but tangent to the origin of the coordinate. As the load increases, this Mohr circle, the size of the Mohr circle increases. When the circle reaches to a point, then this material starts to yield. So can someone tell me what does our Mohr circle look like when the material begins to yield? Can someone tell me? Yeah, when we increase the load, the Mohr circle increases its size. So when it's reaching the yielding point, what does it look like? Can someone describe to me? Tell me where it is. What's this? If this is the circle right at the point where we are about to yield, then what's this? This is normal stress, right? So yes, sigma yt, the yielding stress, yield strength, or yielding strength of the material. Okay, so for metal, it's always like this. Tensile test, and then you enlarge the Mohr circle until you reach this point. Then, whenever it's above, the material is no longer good for us because it deforms permanently. So, it seems like if we can design a material where our stress is less than yielding point, we are in good shape. So that's the easiest concept. The most simplest design equation. Okay? We just make sure our stress is less than yielding strength, then we're okay. But, like what we introduced earlier, we should put a safety factor right here. And usually, n is larger than 1. Because if we don't have this, we may have stress exactly the same as the yielding strength. But if your material has uncertainty, or if your load has uncertainty, and unfortunately, the true load is larger than yielding point, then your material begin to yield. But if you apply a safety factor right here, which is having a value larger than 1, then your design is having a safer gap. So it's like if we are treating the tensile test as our as a design that we're working on. So it's like you only allow this material to have a stress that is reaching up to this point, and over here, for example, this equals to sigma yt over 1.2. So it's like you only allow the pulling force to enlarge until this point. You no longer allow further pulling anymore, because you wish you have this negative and equal sign right here. You don't allow any load larger than this. Then you are having a safer gap between the true yielding. And so for mechanical design, this safe gap between the limit, away from the limit, is important. Okay? So if we can design like this, then let's take a look at how this equation could be changed to a different format. Do you guys remember that we mentioned a material may fail along the shearing plane in the video? Because it's true, because if you are in the material science field, shearing force usually will cause damage along the shearing plane. Okay, so
it's important to understand how much shearing force this material can handle. So if we take a look at the limit state of a Moore circle, where we have sigma yp here. This is the extreme case where a material can survive. And let's take a look at how large your shearing force is. It's right here. This is your maximum shear force. Can someone tell me what's the magnitude of maximum shear at this point? It's very easy. Half of something. Half of yp, yes. So at this point, maximum shear is half of your yielding strength. So for every metal, no matter for what kind of design you have, you can only allow shearing force up to half of your yielding strength. Okay, make sense? Because of this Moore circle, the Moore circle tells you this circle represents the limit state. You cannot survive a low condition greater than the circle. And at this extreme case, this is your shear force. So the largest shear force you can handle would be half of sigma yp, because this is radius, and this is also radius, right? So obviously, the maximum shear you can handle is having the magnitude of half of yielding point. So at the end, you can convert this design equation into a different design equation. Shear force must be smaller than the maximum shear force that you can allow, and it's actually half of sigma yp. With safety factor, if I put an n right here, then I have an n right here. So it's a totally different way to analyze this. If I want to focus on how much stress, normal stress we are facing, then the normal stress cannot be larger than your yielding strength over a safety factor. But if this time I'm focusing on the shearing force, shearing stress, then in this case, you have a 2 right here. Okay, so later on, we call those design models, design equations. Design equations, and they are models, okay, mathematical models. So we will be introducing 3 different models. The first one is called the maximum shear stress model, MSS. The other one is maximum strain energy model, MSE. And the third one is called the maximum distortion energy model, MDE. Okay, so they are 3 different ways to design a material, and their mathematical form are different. Their mathematical equations are different, and you can say this one is the most, I should say, what's the word? Oh, conservative.
Chinese is 保守. And this one is the least conservative. And this one is at the middle. Okay? So since this one is at the middle, in many cases, even in software, they use this model. But this model is the most complicated model in derivation. So please watch my video carefully when I derive this. It's a long process of deriving and difficult to understand. So once you realize, okay, what is distortion energy? And this is the maximum distortion energy model, and I will tell you, people use it all the time. So in the future, when you see something like this, you realize, okay, this software is using this. Okay? Has anyone used ANSYS in the past? ANSYS. Anyone? No? Okay. Has anyone heard of von Mises stress? Anyone? Okay, no, that's fine. That's good. But in the future, when you maybe begin to do senior research, maybe in a graduate program, you may see this for many times. This is very related to this model. Okay, so we will tell you what is von Mises stress. And there's a huge advantage of using this. Very huge advantage. Okay? So that's the last thing I want to tell you today. More introductions about those three models will be shown in the online video.